the previous lecture, we discussed Bloch's theorem, the nature of wave function and periodic potentials, and I had said that I will solve Kronig-Penney model, which is an exactly solvable model. But before doing that, I want to spend some more time discussing the Bloch wave function and its properties and how states are counted and how this leads to an understanding of semiconductors, metals and insulators and their behavior. So, we had discussed that in a periodic potential, the wave function psi k x is of the Bloch form e raised to I k x u k x. I can put a normalization constant in front of it like C n and confine my discussion most of the time to single dimension. However, in general also it is true that in 3D the wave function has psi k, which is a vector quantity as a function of r, is of the form C n e raised to I k dot r u k vector r, where u k is periodic with a primitive lattice vector. So, we also express this vector, again I come back to one dimensional case, psi k x as equal to summation g c k plus g e raised to I k plus g x, and I showed you that this satisfies Bloch form. Let us look at it again. So, the wave function psi k x is equal to summation g c k plus g e raised to I k plus g x. If I put x equals x plus a, where a is the periodicity, then psi k x plus a becomes summation g c k plus g e raised to I k plus g x plus a. If you notice, then e raised to I g a is nothing but e raised to 2 pi I, which is equal to 1. Therefore, a does not really affect the g part of the wave function, and I end up getting that psi k x plus a is equal to e raised to I k a summation g c k plus g e raised to I k plus g x, which is nothing but e raised to I k a psi k x, the Bloch form. So, it satisfies Bloch's equation. Now, I am going to look at it from a different perspective and see what the wave function psi k x becomes if instead I consider psi k plus some reciprocal space vector g prime x. Does it represent something else, and what happens when I make this transformation? And let us look at that. When I substitute k by k plus g prime, this wave function becomes psi k plus g prime x, which will be equal to summation g c k plus g prime plus g e raised to I k plus g prime plus g x. Now, take g plus g prime to be some other reciprocal space vector g double prime, then I have psi k plus g prime at x is equal to summation. Instead of g, now I can add over g double prime and I get c k plus g double prime e raised to I k plus g double prime x. Since g double prime is being added over, it's same thing as adding over g, this is precisely the same as psi k x. So, what do we conclude? We conclude the wave functions psi k plus some g, right, g prime could be any g, x and psi k x are identical. I am underlining this, identical. They are identical. What does it mean? Let us understand that. So, we have said that psi k plus some reciprocal space vector g, if I add a reciprocal space vector g to k, this is same as psi k x. What it means is that k plus g and k are equivalent. I can specify a wave function by k or k plus g, where g is any reciprocal space vector, and this implies that k can be specified within the first Brillouin zone. Let us reflect on that a bit. So, suppose I have this K space extending from minus infinity to plus infinity, and I have this first Brillouin zone here, minus pi by a to pi by a. If I have a wave vector, let us say at this point, suppose this is a wave vector k, this would give me exactly the same wave function if I subtracted 2 pi by a from this and brought it here. This point is for this k, k minus 2 pi by a. In other words, this is k plus g, where g is equal to minus 2 pi by a. Let us look at another point, let us say here, even outside minus 2 pi by a. Let us say this point is over here. I can translate it by adding 2 pi by a to this, and if I do that, I would have moved it somewhere here. This is 2 pi by a, this way. This point is some k, and this point would have been k plus 2 pi by a. I made a slight mistake here. This point k plus 2 pi by a does not come here. So, I am going to cut it with a fine pen. It actually moves somewhere here. So, I am going to make it again. This point moves over here. So, it is this point which is, erase this, k plus 2 pi by a. Nonetheless, the point is that by adding appropriate reciprocal space vector, I can bring all the k points to the first Brillouin zone, and that is enough to specify a wave function. So, let us write it again. We can bring any k to an equivalent k point within the first Brillouin zone, and that is enough to specify a wave function. Now, this should remind you of something. Let us write that. This reminds us of phonons. What happens in phonons? In phonons also, k within the first Brillouin zone was sufficient or enough to specify any phonons, any phonon. So, k and k plus g gave exactly the same vibrational mode, and this happens in electrons also. So, this is a general property of waves, be it vibrational or Schrodinger wave. In a periodic structure. So, if you have a periodic potential, periodic lattice constants, things like those, k within the first Brillouin zone is enough to specify any wave in that structure. Let us now look at some examples through this. First example of free electrons. Remember what we have done so far in discussing free electrons, and after that the nearly free electron model is that if I look at the free electron E k versus k curve, and here is the boundary of the first Brillouin zone, here is the second one, this is how the black curve, this is how the free electron curve looks, and when I apply nearly free electron model, the energy curve changes a bit near the boundary, and I am making it here schematically, and then in the second zone it goes like this, in the second zone it will go like this, and so on. And if you recall from the lectures earlier, I can translate all this into the first Brillouin zone, and I had said that I owe you an explanation for this, and this is what I am explaining right now. So, let me make this figure more accurately in the next slide. We tried doing that here. So, here is the curve, and let us make the first Brillouin zone, which is right here. And the second Brillouin zone, which is right here. And I said that the curve becomes something like this. the actual energy curve when I do nearly free electron model. In the second zone, it will again split here by 2 Vg and it will become like this. So, let us make it here, it will become something like this. And when I translate this into the first Brillouin zone, remember how we translate the points. The point out here would be translated by 2 pi and it will go to this point right here. Similarly, point out here will become equivalent to this point and this will also come here. So, what happens now is that this curve, this point is translated here, this point would be translated here by 2 pi. Let me make it more clearly. This point out here on the right side gets translated here. So, what you see now is that this curve will become like this, and when the other part gets translated, it will become like this. So, here is your band diagram or energy versus k diagram in the first Brillouin zone. And if I were to extend, let us say I want to say, let me also make these points. This is k equals pi by a, this is k equals minus pi by a, the blue ones is k equals 2 pi by a, the blue one out here on the left hand side is k equals minus 2 pi by a. If I were to see, no, let me see it in the whole k space, then what I would do is k plus g is equivalent to k, and therefore, this curve would start behaving like this, because all these points are equivalent. The orange curve, the upper band, would start doing this. When I bring all the curves only within the first zone, then it is called reduced zone scheme. I am looking at all the bands in the first zone. If I plot them over the entire k space, although it is not fruitful, but sometimes it goes good to visualize things, this is the extended zone scheme. If I remain within the reduced zone scheme, so suppose I do not look at left and right, here I would put the energy as E as a function of k, but it is as a function of k for each band, then I will label the band as E n. For example, the blue one here would be E 1 k, the orange one would be E 2 k, and so on, and the higher bands. So, it becomes E n as a function of k within the zone. Let me now make this diagram once more to make things clearly visible. So, I had this curve for E k equals h cross square k square over 2 m, and in the reduced zone scheme, let me make this zone extended like this. I have these bands like this, next one will be again like this, and so on. This will be E 1 k, this will be E 2 k, third one will be E 3 k, and so on. And if I want to extend them further, they will go like this. Does not teach me anything new, but nonetheless sometimes good to visualize what is happening. So, either suppose I am going from left to right, let me look at band 2. If I am going from left to right, let me make this arrow. I can go to the right starting from point minus pi by a to plus pi by a. I can go to the right, I am showing by this dashed line, go to the right, reach the point plus pi by a. In the extended zone scheme, I will go further and increase k, or in the reduced zone scheme, I will say that this point which I am showing by a cross is again equivalent to this. So, I can come back to this point, start all over again. So, I can keep repeating myself periodically within the first zone, because the point pi over a and minus pi over a are equivalent. So, in the reduced zone scheme, I go to pi over a and jump back to minus pi over a, because that point is equivalent to pi over a, or in the extended zone scheme, I can keep extending k, but that is exactly the same as k minus pi by a. So, I can always come back. So, this is how you look at k. If you have noticed carefully, you must have seen that when I made this graph, I will just make the bands now within the first Brillouin zone. Since the band repeats itself, is either a minimum or a maximum at the zone boundary, and therefore, E k versus k has slope equal to 0 at zone boundaries. Very important point. Now, I said this in the context of 1D, the same thing happens in 2D or 3D also, except that this is slightly more subtle, because you have to now think of the band structure in 3 dimensions. I will comment on that a little later. It will be interesting to see what happens if I look at the free electrons in reduced zone scheme. So, let us do that. I have this curve of free electrons in the reduced zone scheme, in the extended zone scheme, and suppose now I say I want to bring it to the reduced zone scheme. I may want to do that before I even apply the Bloch's theorem or the perturbation theory or nearly free electron model. If I do that, so in the first zone, the zone is shown here with blue lines. So, this is extending from minus pi by a to plus pi by a. In the first zone, which I have been making with blue, the energy diagram looks like I have shown with blue out here. For the second zone, I will bring this fellow back by 2 pi by a, and the fellow from the left hand side to the right, moving it by 2 pi by a, and the curve would look like this. In the third zone, again I will do the same thing, and this I will leave for you to see. The curve would look like this. So, this is what I have made within this is free electron energy in reduced zone. Now, let me repeat it in the next slide. So, what I have done is I have taken these free electron energies and plotted them in the first zone by translating all the energy curves. So, they look like this. The third zone will look like this, and so on. Now, let us see what happens when I turn on the perturbation or turn on that weak potential. This curve starts developing a gap. I am showing it by black now, a gap near the zone boundary. The upper one will go up and it becomes smooth near the zone boundary. The next one again will become smooth near the zone boundary and become perpendicular to the zone boundary with 0 slope near the zone boundary. So, this is E 3k, E 2k, E 1k, and here are the gaps. Here is the gap. So, you see very clearly, if I put all this nearly free electron model, free electron energy in the first zone, and then I apply the perturbation or the periodic potential, how the bands evolve within the first Brillouin zone itself. And then of course, if you want to make it in the extended zone scheme, you can always extend it. So, I have given you a picture of how we can think of all the wave functions in a periodic structure being equivalent if their wave vectors k differ by a reciprocal space vector. I have shown it in 1D and 3D also the same thing happens. So, in 3D psi k vector r is equivalent, in fact the same, right, as psi k plus g r, and therefore, I can make all the pictures, energies and everything within the first Brillouin zone. So, let us write that also, and this implies all calculations etc. can be done considering k within the first Brillouin zone. True for 3D also. Having discussed this, now let us understand the significance of wave vector k in 3D and k in 1D. Question: in free electrons, k or h cross k to be precise gives the momentum of the electron under consideration. Because here when I have psi k r, which is some normalization constant e raised to I k dot r, if I apply the momentum operator to psi k r, this is h cross over I gradient of C n e raised to I k dot r, it gives me h cross k times the wave function psi k r. So, this is a momentum eigenfunction, and therefore, it gives the momentum of the electron. On the other hand, if I look at momentum operating on psi k of the Bloch form, it is h cross over I del operating on e raised to I k dot r times u k r, and this is not equal to some vector p 0, let us say, times psi k r. Therefore, it is not a momentum eigenfunction. So, question is, in the free electron, this gives h cross k gives the momentum of the electron. What happens in a Bloch electron case? So, let me complete this question. So, what does k specify in case of an electron in a periodic potential? I am continuing this question from the last slide. So, I will just previous slide. So, I will just say this is question continued. So, we just saw that in case of free electrons, h cross k is the momentum of an electron, and the question we are raising it, what about when the wave function is psi k of the form e raised to I k dot r u k r, or in 1D it is of the form e raised to I k x u k x in 1D. I am right now not proving anything, but the answer to this is h cross k behaves exactly like 1D. 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 H cross k like the momentum of an electron or the particle in a periodic lattice. So, that is the answer. So, although P operator psi k r is not equal to some P 0, which is the eigenvalue for the momentum psi k r for psi k equals e raised to I k dot r u k r. So, it is not a momentum eigenstate. Still, H cross k behaves like the momentum of an electron whose wave function we are writing, or a particle in periodic potential. What does this mean? So, question is, although I am saying that it is behaving like the momentum, what does this mean? This means that if I take d by dt of H cross k for an electron or particle moving in a periodic system, this will be equal to the external force. And let me tell you why I am calling this external force. This is external to the system. That means, it is not including that periodic potential, but the force that I am applying from outside. It could be the electric field, for example, an electric field. So, that is one way that think of this as the momentum. The other thing is that it is conserved. If I have some impulse imparted to this electron through phonons, through whatever, right, this will give you H cross k 2. So, it is in these two ways that it behaves like momentum, and we will see examples of this later when we do little bit of transport. So, to conclude this lecture, we have shown that k within the first Brillouin zone is enough to specify the wave function psi k r or psi k plus g, it does not matter, the wave function of a particle in a periodic potential. Number 2, what we have shown is therefore bands of energies are labeled as E n k. K is within the first Brillouin zone. Each band now is given this index n equals 1, 2, 3 and so on. And we showed through the example of the free electron and nearly free electron energy curves how everything gets reduced in the first Brillouin zone, and the wave vector k behaves as momentum quantum number, that is H cross k can be thought of as momentum of particle in the system. And therefore, H cross k, now let me give you the name also, is given the name H cross k is given the name of crystal momentum. So, we have introduced the idea of crystal momentum also. So, let me on the side show this. This part is the wave function and energy in the reduced zone scheme, and the second part is the introduction of crystal momentum of a particle in periodic potential. So, these are the new things that we have introduced. In the next lecture, we will see how we count the number of states in a band and how the gaps lead to the behavior of metals, insulators and semiconductors. Thank you.